Hello everyone, my name is Julien Kammer and I'm a postdoc from University College Cork in Ireland, and I will talk about the characterization of SOA from the reaction of Guaiacol with OH and nitrate radicals in different conditions. So I presume that everybody knows that the atmospheric particles affect the climate, but also the human health, and especially in urban areas where residential solid fuel burning is one of the major sources of particles. Here is just a picture to illustrate this fact. I took this picture from a field study conducted in Dublin that aimed at investigating the chemical composition of organic aerosols during two wintertime pollution events. And what is clear from these two pollution events is that oil, peat, coal, and wood burning are a dominating fraction of the organic aerosol, illustrating that residential solid fuel burning is really important. We also conducted a field campaign last year in Cork in January 2019, and we observed very strong level of PM2.5 that are represented here in black in microgram per cubic meter, and you can see that there's some increase at night time, and it can reach very high level up to 180 micrograms per cubic meter. We also measured with anhydride some precursors, some monoaromatic precursors, such as here glycols and methoxyphenols that are represented here in blue and red on this graph. And you can see that both compounds really tracked timeline of PM2.5, suggesting that residential solid fuel burning is really important. We also measured some nitro compounds such as nitrocadicol or nitroguaiacol, and again, both roughly follow the timeline. So if you want to know more about this field campaign, I invite you to attend to Nial O'Sullivan talk, which is on the 2nd of September. So from this field campaign, if we look at the diurnal ratio, the mean diurnal plot, of the guaiacol and the nitroguaiacol, we can see that both compounds roughly have the same diurnal trend, and especially they increase at the same time during nighttime, meaning that they probably have very important primary-like emission. However, if you look at the decrease here, you can see that there's a small difference. So if you plot the ratio of the nitroguaiacol versus the guaiacol, you can see that this ratio increases at night, meaning that there's a source of nitroguaiacol, so probably secondary chemistries that are producing this nitroguaiacol. So here's the question: are the nitro-oxygenated compound most primary or secondary origin? So that motivated our study to investigate the oxidation of solid fuel burning traces. So here we selected one monoaromatic traces, which is the 2-methoxyphenol, also called the guaiacol. And this we want to investigate the reaction of the guaiacol with several atmospheric oxidants, the OH, ozone, and nitrate radicals, and the potential SOA formation using an atmospheric segmentation chamber. And the idea is to look at the effect of environmental conditions and identify the different products formed in both gaseous and particulate phases, and compare that with the literature. So here's the experimental setup. You can see here a nice picture of the atmospheric chamber that has been used for this study, which consisted in a 2.7 cubic meter cylindrical atmospheric chamber, which is made with Teflon. This chamber is also equipped with some lamps, such as UV visible lamps and UV lamps, and also connected to different instruments, a Figaro-Topsims to investigate the chemical composition of the gas phase and the particle phase, and ozone and NOx monitors, an SMPS to track the particle formation, and a sensor to get the temperature and relative humidity. So we conducted several experiments. We started by investigating the photochemistry by exposing guaiacol to UV, then the reaction of guaiacol with ozone and O'. Then we moved to the reaction of guaiacol with OH in different conditions, then the reaction of guaiacol with nitrate, and we stopped our experiment due to the COVID-19 pandemic, because the laboratory was closed. So we have here a limited data set, but we already have interesting results that I will present now. So all our experiments was performed without any seeds, and from the first experiment with UV, ozone, and the O', we didn't observe any significant reaction and didn't observe any new particle formation. However, then when we move to OH oxidation, we always observe new particle formation that are traduced by this graph. So here is, for example, the diameter along with the experiment time, and the color scale represent the particle concentration. And here you can see that at some time, a huge concentration of small particles appeared and then grows during the time, traducing the processes responsible for new particle formation. And you can see this typical banana shape for different conditions of the Guaiacol and OH reaction. So then we move to study what are the chemical reactions at the origin of this new particle formation. So here's a typical experiment we conducted at low NOx and with 30% relative humidity. So here you can see again particle number and size distribution. In red is the timeline of the Guaiacol, and in blue is just the timeline of one oxidation product. What is clear here is that as soon as we inject Guaiacol in the chamber, it increased fastly and reached equilibrium and stays stable for a couple of hours. And then as soon as the UV light are turned on, OH is produced, and we can see the decay in Guaiacol due to its consumption by OH radicals. And at the same time, for sure, there is an increase of the oxidation products. And what is interesting to see here is that the particle formation started very, very quickly after the UV is turned on, so meaning that we have a very fast chemistry and very fast particle formation. So here we detected also other products. So here that was a C6 product. I also here plotted in purple a C6H6O3 as well as a C12 product, which is probably a dimer, and you can see that both products here increased at the same time as the C6 products here on the top graph, meaning that even the dimer increased quickly after the UV is turned on, meaning that the chemistry is very fast here. So we also look at all the compounds that were formed during this oxidation. So we focused only on iodide cluster to avoid any misinterpretation, due to possible crossed ionization with, for example, NO3- in the IMR. So if we look at these top 20 compounds detected as iodide cluster, we can see that the first products are mainly C6 compounds. So if you remind the structure of the Guaiacol, it's the C7 compound, so it means that these products, there is a loss of carbon and very probably a loss of the methoxy group. We also observed some C7 compounds, which are the retaining structure compound, and some dimer here represented in green, and the other products are small, very oxidized compounds. So illustrating here that we have a very rich chemistry producing a lot of different compounds. So we compared this experiment that is conducted at very low NOx, but in the presence of 30% relative humidity, to an older study from Yi et al. In 2015. They studied the oxidation of the Guaiacol in low NOx and dry conditions. And they observed from this reaction of the Guaiacol here that and they probed the mechanisms, and that lead for mostly C7 compounds, and some of these C7 compounds have been detected also in our experiment, such as C7H8O3 or C7H8O4. But the main product we detected here has been also detected in their study, but just as a minor compound, and they didn't propose any mechanism for the formation of this compound, which is the catechol. And we also observed a range of C6 compounds that are the major compound in our study that was not reported here. So it seems that by comparison to the dry experiment, we hear the increase of relative humidity favors the formation of C6 compounds. So we look at the mechanisms for the formation of the catechol, and we found that the recent study by Sun et al. Proposed the mechanisms based on theoretical study. And so they proposed that the H abstraction of the methoxy group, which is the most favorable H abstraction on the Guaiacol, produces a peroxy radical from the addition of O2, and then it can stabilize even with small amounts of NO, and goes for an alkoxy radical that decomposed into this radical that leads to the formation of the catechol. So that provides an explanation for the mechanisms formation of the catechol, but didn't explain at all why the water would favor this formation pathway. So we have to go into this mechanism and understand a bit more to understand why the relative humidity may favor the C6 formation. We also compared the products from this experiment, which is low NOx and humid conditions, to other experiments we conducted with OH. So this experiment was conducted with the same amount of relative humidity but with higher NOx. And we can see here that most of the products are nitrogen containing compound, which makes sense, and which means that we have the formation of nitro-oxygenated compounds, such as here nitro-guaiacol or nitro-guaiacol. And if we compare this experiment to the same experiment but in dry condition, we can see here that the two top compounds are the same, but the order is inversed, and the top compound is from far the nitro-guaiacol. So it means again here, if we compare these two experiments, that the humid conditions seems to favor the formation of C6 products. So just to conclude, so here we investigated the reaction of guaiacol with several oxidants, and we have only reported new particle formation from OH oxidation. We have seen that in low NOx and humid condition, most of the products are C6 products, meaning that we have a very important formation of products with the loss of the methoxy group. And in high NOx condition, we identified the formation of nitro-guaiacol, which was expected based on the literature, but what was not expected is that in humid condition, when your relative humidity is 30%, nitro-guaiacol is not the main oxidation product. So in terms of atmospheric implication, it means that nitro-catechol is not only a tracer from catechol oxidation, but also from guaiacol oxidation, when relative humidity is at least 30%. And it is clear that the humidity changes the chemistry and the products observed. And once that will be more characterized, I think it was to be included in future modeling studies of biomass burning. So in terms of outlook, we have to just repeat some of our experiments to just confirm our results, complete the experiment with missing conditions such as dry and low NOx conditions, and investigate the chemical composition of particles using our Figueroa sims. I just want to conclude by acknowledging all the team and the fundings and you for your attention.